I'm just going to record 4.3. I'll upload everything later. Okay. So 4.3 is all about what derivatives of functions can tell us about the functions themselves. Let me show you what I mean by that. So this is like the first question for 4.3. Suppose we're given a formula for a function f. So we're going to have a function f of x. We have some sort of equation for f of x, right? So first thing asks, how can we determine where f is increasing or decreasing? What does that mean? What does increasing or decreasing mean for a function? Well, you kind of already know, don't you? Let's graph it. This function's increasing. This function's increasing. This function's increasing. Increasing just means that for every x value, its y is bigger than the y of the x values that came before it, and less than the y value of all the x values after. So like, let's take this point. For whatever x value this is, the y value we get out of it, the f of x, it's bigger than the ones before, and it's less than the ones after. Take this point, bigger than the ones before, less than the ones after. Take this one, bigger than the ones before, less than the ones after. This is what increasing means. Seems reasonable. Another way we could think about it is positive rate of change, positive slope. Our tangent lines are pointing up and to the right, if that helps. It's positive slope. That's increasing. Similarly, this function is decreasing, and so is this one, and so is that one. Decreasing, our y values are going down. As x gets bigger, y gets smaller. Take this point on this curve, its y is less than the ones before it, and bigger than the ones after it. Same here, same here. Another way you can think of it as these points, at these points, the slope of the function is negative. Our tangent lines are pointing down and to the right. Increasing is up and to the right, decreasing is down and to the right. Y value is getting smaller. Okay. Increasing, decreasing. Now, how do we tell if a function's increasing or decreasing? Well, we mentioned that it's related to the slope at a point, right? What's another word for slope at a point? The derivative. Remember how the derivative is defined. At any point, it is just the slope. Oops. That should be an H. So let me erase a fair bit of this. The derivative equals the slope between 2 points of the function as we bring them closer and closer and closer and closer together. Derivative is just slope at a point. This here, the slope of this tangent line, is the derivative at that point. Okay, so how do we tell if a function is increasing? Well, if a function is increasing, its slope at its points are positive. Its derivative is positive, above 0. And if a function is decreasing, then its slope at a point is negative. Its derivative is negative, below 0. This is something where I might graph it out, unlike Desmos, might make one of those toys I make on occasion. But how do we tell if a function is increasing or decreasing? We see if its derivative is positive or negative. Let me write that up. If the derivative of f of x is greater than 0, we're increasing. Our y values are going up. And if our derivative is less than 0, we are decreasing, our y values are going down. So that's one thing we can tell from derivatives, right? Okay. Now, concave up and concave down. Still doable, a little bit more complicated. So, concave. What does concave up mean? Means it looks like a bowl. Let me write that. So CC up, we're going to call that concave up. This function is concave up because it's like, we could fill it. Concave, not convex. Let me erase some of those lines. That's just a demonstration. And we'll just redo it. Okay. Another way you could think about it is our tangent lines are below the curve for our function. Similarly, CC down means concave down, like some sort of dome. And here our tangent lines are above the curve. Okay. So that's what concave up and concave down means. How can we tell if our function is going to be concave up or concave down? It's like knowing the curve of things. That could be handy for us, right? Look at the tangents. Tangents on this left-hand side are slopes. They start negative, go to 0, and become positive. Our slopes are increasing. Our derivative is increasing. Over here, concave down. Slope starts off positive. Derivative starts off positive. Gets less, 0 starts becoming negative. It's decreasing. Okay, so if our function is increasing or decreasing when the derivative is bigger than 0 or less than 0, how can we tell if our slope, if our derivative is increasing or decreasing? We're going to take the derivative of that. It's the same thing, except now we're taking the derivative of a derivative. So, we are concave up if the second derivative is bigger than 0, if our slope is increasing. And we're concave down if our second derivative is less than 0, if our slope is decreasing. Another way you can think about it that might be handy, this second derivative is just the derivative of our first derivative. It tells us when our slope is increasing or decreasing rather than the function itself. So that's something we can tell from, that's how we can tell if the function is concave up or concave down at a point. We check the second derivative. Now, how do we locate inflection points? An inflection point is just a place where our concavity changes. How do we tell where our concavity is changing? We're going to find critical points like we do for the first derivative, except now we're doing it for the second derivative. We're setting our second derivative equal to 0, and then, and only then, we're checking to see if our concavity is changing. So here's an example. Pardon me. Trying to think of a good example. Okay, here's one. F of x equals x times x minus 1 times x plus 1. If you graph it, it looks kind of like this. Ooh, like that. This is going to be negative 1. This is going to be 1. And this, of course, is 0. Okay, so where is this concave up? Well, looks like it's concave up from 0 to the right. It looks like a normal bowl shape. And here, from 0 to negative 1 and beyond, from 0 to negative infinity, looks concave down, upside down bowl shape. Okay, so let me multiply this out real quick. minus x. We're going to take the first derivative. That's going to be 3x squared minus 1. And then we're going to take the second derivative. That is going to be 6x. Where is 6x bigger than 0? Where is our second derivative bigger than 0? Where is our second derivative bigger than 0? Where's our function, I should say, where's our function concave up? Where this is bigger than 0, where x is bigger than 0. So from here onwards, concave up. Where is our second derivative less than 0? Where is our function concave down? Well, that's for all the negative values of x. So we can set our second derivative equal to 0, x equals 0, and then if we look at the points on either side of 0, we're concave up over here, we're concave down over here, x equals 0 is where the concavity changes. That's an inflection point. So those are like the three things we can tell from derivatives. We can tell some more things as we do like higher directions, but those are the three things for right now that we need to worry about. And I'll show you some problems where we can use those to our advantage. Hang on. Okay, here's the second example problem. Find the intervals, find like just the spaces on the number line, where f of x equals 2x cubed minus 15x squared plus 24x minus 5 is increasing or decreasing, where our first derivative is positive or negative, and find local extrema, local maximums and minimums. Okay, so first, let's find where our function is increasing or decreasing. How do we find where our function is increasing or decreasing? We find where our first derivative is positive or negative. How do we do that? First, we find our first derivative. Generally, just for this whole chapter 4, generally first thing you should be doing, finding the first derivative. That's 3 points from me. Just find the first derivative, sometimes even the second derivative. First derivative for this one is 6x squared minus 30x plus 24. Now, we want to find where this is increasing. So we're going to say that 6x squared minus 30x plus 24 is bigger than 0, and we're going to solve for x. 6, we're going to divide both sides by 6. X squared minus 5x plus 4 is bigger than 0. If we factor this, we get x minus 4 times x minus 1. Okay, so the derivative is bigger than 0 when this product of x minus 4 times x minus 1 is positive. So we need either both of these to be positive, or we need both of them to be negative. Okay, seems reasonable enough. Well, if x is bigger than 4, then both of these are going to be positive. If x is between 1 and 4, this is going to be negative. This one's going to be positive. A negative times a positive is still a negative. So that's not going to work. But if x is less than 1, then both of these are negative, and the product is positive, and we're bigger than 0 again. So where is our function increasing? Where x is bigger than 4 and x is less than 1. Cool. We could factor this and do the same thing for decreasing, but another way we could do this is with a table or a number line. Okay, so this is the derivative. What do? We're going to set the derivative equal to 0. We're going to find critical points. x squared dividing by 6 doesn't do anything. Squared minus 5x plus 4 equals 0. And by the same math we did earlier, this implies that x equals 1 and x equals 4 are critical points. Okay, so these are places where our derivative equals 0. These are places where our derivative can change from positive to negative, because if our derivative is at 0, then we can tip one way or the other. So we're going to set up a number line. 1, 4. And we want to find where the function is increasing or decreasing. So what we're going to do is we're going to take number values from each part, we're going to plug them into this derivative and see what we get. Let's say we take 0 because it's less than 1. If we plug 0 into this, we get 24. F of 0 is bigger than 0. F of 0 is positive. Well, not f of 0. F prime of 0. The derivative at 0 is positive. So, due to some stuff that we know about continuous functions and differentiable functions that we're not going to get into the theory of right now, all of the points, all of the x values less than 1 have a positive slope. The derivative is bigger than 0, so our function is increasing. Let me draw it. Function's going up. From negative infinity to 1, it's going up. And then it's 0 at 1. What happens between 1 and 4? We pick a number between 1 and 4, and we plug it into the first derivative. Let's say we do 2. Well, 6 times 2 squared, this is 24, plus 24 is 48. If we plug 2 in here, we get 48 minus 60, that's negative. For all the points between 1 and 4, the slope, the derivative, is negative. Our function is decreasing from 1 to 4. And the derivative equals 0 at 4, so we have a little flat. And then finally, from 4 to infinity, we're going to plug in any number we want, could be 1,000,000, and we're going to see this is positive. Our function is increasing. Again, the derivative is bigger than 0 whenever x is bigger than 4. So our function is going up. Our y values are increasing. So, let me put those intervals down. We are increasing from negative infinity to 1 and from 4 to infinity. And we are decreasing, apologies for the handwriting, from 1 to 4. Okay, so that's cool. We figured out where the function is increasing or decreasing. If you want, you can graph this, plug it into Desmos or whatever, and you can see the places where it's going up or going down exactly match this. This is like a rough graph of like, is it increasing or decreasing? It's not meant to look exactly like the function, just tell us, are we going up or are we going down? Now, where do we find local extrema? Where do we find like those little places that aren't necessarily the highest or the lowest, but are the highest or the lowest of all the points around them? The first derivative tells us. If we go up and up and up and up, flatten out, and then we start going down again, then whatever this point is, where we stop going up and start going down, that is a local maximum. It's like throwing a marker through the air. It's going to arc, it's going to reach a point at the top where it's as high as it's going to go, start coming back down. This is a local maximum. There's a local maximum at x equals 1, and it has a height of f of 1. We would plug 1 into the original equation to get the height of this local maximum. Similarly, at 4, we have a local minimum, because that's the part where we can't decrease any further. We turn around and start increasing again. So this is as low. This is the lowest of all the points around it. Again, check this in a graph. but we can say there's a local minimum at x equals 4 with a height of f of 4. We're going to plug 4 into this original equation. That's how we find the intervals where a function is increasing or decreasing, and that's how we find local minimums and maximums. We take the first derivative, we set it equal to 0 to get the places where the function's flat, and we're going to make a number line. We're just going to test some of the points in between back in our first derivative. 0, if we plug 0 into this, we get positive. If we plug 100 into this, we get a positive number. If we plug 2 into this, we get a negative number. And that's how we figure out if our function is increasing or decreasing in between those critical numbers. Okay. Let's do another example. Okay. New problem, same task. We're given a function, x to the 2/3 times x minus 3. And we want to find where that function is increasing or decreasing. We want to find those local extrema. Okay, how are we going to do it? First, we take the first derivative. There's a couple of ways you could do this. You could do a product rule here. I'm not going to do a product rule here. I'm going to multiply it out first. So we get x to the 5/3 minus 3x to the 2/3. And then I'm going to take the first derivative. Either way works. Do whatever works for you. This is just how I think about it. This is going to be 5/3 x to the 2/3 minus 2x to the negative 1/3. Power rule. A little bit more complex because we got fractions, but that's about it. So, next question. What are the critical points? Where does this equal 0? Where does it not exist? Well, derivative, first we're going to set it equal to 0. 5/3 x to the 2/3 minus 2 over x to the 1/3, because that's what a negative exponent means. Let's solve for x. We're going to have 2 over x to the 1/3 equals 5/3 x to the 2/3. Okay, so that's something. We're going to multiply both sides by x to the 1/3. So we get 2 equals 5/3. We get 2 equals 5/3 times x. And by extension, we get x equals 6/5. So when x equals 6/5, our derivative equals 0. Neat. Now, also, something we have to consider, where does the derivative not exist? Because that's critical points too. Our derivative has an x in the denominator. So when x equals 0, that first derivative doesn't exist. We need to think about that one as well. We're going to graph this one later, or at least I'm going to talk about concavity, and this gives us an interesting graph thing that I can show you all. But for right now, key things. X equals 6/5 gives us a derivative of 0. That's a critical point. X equals 0. Derivative doesn't exist there. That's a critical point. Let's make a number line. 0, 6/5. Okay. So let's plug some points into our first derivative to figure out where we're increasing, where we're decreasing. From 0 to 6/5, what's the number in between there? 1. The derivative at 1 is 5/3 minus 2, negative 1/3, negative. We're decreasing from 0 to 6/5 because the derivative at 1 is below 0. And if the derivative is below 0, our function is decreasing. What if we plug in something less than 0? Well, in that case, let's say we plug in, I don't know, what's something that has a good cube root? 1,000. Let's say we plug a negative 1,000 into our first derivative. Just spitball it. Well, this would be negative 2 times negative 10. This would be 20. We would have negative 10 squared, 100. So we have a positive plus a positive. Reason about this however you will, is just the way I think about it. This is positive. Our derivative, when we're less than 0, is bigger than 0. Our function is increasing from negative infinity to 0. You can draw it like there's a slope going up. Derivative doesn't exist here. You can draw this however you want. I like to leave a little hole. We're decreasing from 1 to 6/5. Derivative equals 0. We flatten at 6/5. And then last but not least, what happens past 6/5? Well, we can do the same sort of test. We can plug in like x equals 1,000, because it has a nice cube root of 10, or plug in whatever, really. And we're increasing. We're increasing for all the x values past 6/5. Okay. So, where's our local minimum? Where's our local maximum? Do they exist at all? We know where we're increasing and decreasing. Wait, note those down. We're increasing from negative infinity to 0, and from 6/5 to infinity. And we're decreasing from 0 to 6/5. Cool. So where are our local extrema? Well, we definitely know where our local minimum is. Right there, right? We go as low as we can, derivative of 0, we flatten out, and then we start increasing again. This is a local minimum. It's at x equals 6/5. If you want the height, you plug 6/5 into the original equation. What's happening here? This is the interesting one. Now, the derivative doesn't exist at 0. That doesn't mean it's an asymptote. That doesn't mean we're just shooting off to infinity. This can be a corner. This can be a cusp. If we plug 0 into this function, we get a height of negative 3. Actually, no, we get a height of 0. Forgive me. Like when we do the product, we get a height of 0. This point exists for the original function, but doesn't for the derivative. So this is a corner. This is a cusp. The derivative doesn't exist, but the function's defined. And when we approach that point, when we approach that 0f of 0, that point wherever it is, we're increasing all the way up to it, and then we're decreasing all the way from it. So whatever f of 0 is, it's the highest of the points around it. The derivative doesn't exist there, but that doesn't matter. The important thing is we're increasing up to it, the point itself exists, and then we're decreasing away from it. So this is a local maximum. It happens at x equals 0. It happens at 0f of 0, but the derivative doesn't exist. If you graph this, I'll show you this later. But if you graph this, we get a nice cusp. We get a nice little corner that we can't take a derivative at, and that's why this looks a little weird. But that's our local maximum, and this is our local minimum. Same process for every type of problem. I might do the quiz problem later. We'll see. Hang on. Okay. Another problem. This one's a little different. We're given a function, x cubed minus 3x squared minus 9x plus 4. What do we want to do? We want to find where this is concave up or concave down, and we want to find the inflection points. We want to find those places where the concavity changes. How do we do that? Well, increasing and decreasing is a first derivative thing, right? So concavity is a second derivative thing. We start with finding the second derivative. Our first derivative is 3x squared minus 6x minus 9. And then, what's our second derivative? Derivative of the first derivative. We take the derivative again. 6x minus 6. Okay. Where can it change? Where can it change from positive to negative? We're going to set it equal to 0. 6x minus 6 equals 0. 6x equals 6. X equals 1. That's the only place. Okay. We're going to do the same thing that we did for the first derivative. We're going to take a point less than 1. We're going to take a point from each interval. We're going to take a point less than 1, and we're going to plug it into the second derivative. And we're going to take a point bigger than 1, and we're going to plug it into the second derivative. And we're going to see if we're concave up or concave down. Let's take the point 0, right? If we plug 0 into the second derivative, we get -6, which is negative. For all the x values less than 1, we are concave down. Upside down bowl. And then we're going to take a value bigger than 1, let's say 2. 6 times 2 is 12, minus 6 is 6. Positive. Concave up. For all the x values less than 1, we're concave down. For all the x values bigger than 1, we're concave up. So we're concave down from -infinity to 1. We're concave up from 1 to positive infinity. And what's our inflection point? It's the place where concavities change. X equals 1 is our inflection point. That's it. Whenever we ask for concavity and inflection points, this is what we're doing. Same thing as increasing and decreasing, just now we're doing it with the second derivative instead of the first. I'll show you another example. I'll show you 2 other examples, in fact. New function, same goal. F of x equals natural log of x squared plus 5. We want to know where it's concave up or concave down. We want to find where the concavity is changing. Inflection points. First, we're going to take the first derivative. Second, we're going to take the second derivative. This one's a chain rule. 1 over x squared plus 5 times 2x. 2x over x squared plus 5. We're going to take the second derivative. This one's a quotient rule. We're going to have low d high minus high d low over low squared. And I'm going to simplify this out a little bit. Give me a moment. Okay. Second derivative, negative 2x squared plus 10 divided by x squared plus 5 squared. Okay, so what points are we looking at? We're looking where the second derivative equals 0 or doesn't exist. No square roots, no natural logs, and the denominator can never equal 0, so we don't need to worry about it not existing. Where does the second derivative equal 0? We're going to set the numerator equal to 0 and find out. We end up getting 10 equals 2x squared, and to make a long story short, x equals plus or minus the square root of 5. So that's like negative 2.236 and positive 2.236. Okay, so let's put that on a number line. Negative root 5, positive root 5. Where is it concave up and concave down? We're going to plug in a point from less than negative square root of 5. We're going to plug in a number between these two, and then we're going to plug in a number bigger than square root of 5. And that'll tell us concave up and down. Okay, so first let's do one in between. We're going to do 0, nice and easy. Second derivative, if we plug in 0, we get 10 over something that's always positive. We're concave up between these two. What happens if we plug in something bigger than 5? Well, in that case, bigger than the square root of 5, I should say. If we plug in something bigger than the square root of 5, the denominator stays positive, but the numerator becomes negative. So we end up with something concave down. And same deal over here. Where is the natural log of x squared plus 5 concave up? Between negative square root of 5 and square root of 5. Where is it concave down? From negative infinity to the negative square root of 5, and from the square root of 5 to infinity. Where's our inflection points? Where does the concavity change? Negative square root of 5, positive square root of 5. Again, I recommend graphing any of the things you're practicing with, because that can really help build an intuition about where a concavity is changing and if you're calculating it correctly or not. Another example. Blimey, this one looks familiar. F of x equals x to the 2/3 times x minus 3. This was the weird one from earlier, remember, where it's increasing, decreasing, increasing, but the derivative doesn't exist at 0. Now we want to know, where's it concave up? Where's it concave down? What are the inflection points? Well, I took the liberty of rederiving the first derivative and getting, through the power rule, the second derivative. Now we're going to set it equal to 0. We're going to solve for x. We're going to find where the second derivative equals 0 or doesn't exist at all. And we're going to use that to find concavity. First, we're going to set that second derivative equal to 0. And we're going to solve for x. If we multiply both sides of this by x to the 4/3, is it 10? Jeez. Never mind. If we multiply both sides by x to the 4/3, we get negative 2/3 equals 10/9 times x. And then we're going to solve for x. X equals negative 2/3 of 9/10 is negative 6/10. Yeah. So when x equals negative 6/10, the second derivative equals 0. Pretty cool. And also, where does the second derivative not exist? Surprise, surprise, x equals 0. We have negatives for exponents. We have x's in the denominators. X cannot equal 0. So that's another critical point. Okay, so we're going to have negative 6/10, and we're going to have 0. And, as always, we're going to plug in points from these intervals, see what's going on. Okay, so if we plug in a number, man, this is going to be a pain to plug things in. This happens on occasion. Things are just a pain. If we plug in 1,000, if we plug in negative 1,000, the cube root is negative 10. This ends up being negative 1/9. This over here ends up being, so that one's negative 1/9. This one's going to be absurdly, no, it's going to be smaller. You know, give me a moment. I'm going to work this out. Turns out this problem's like way easier if you can just remember that negative 1's cube root is negative 1. That's way easier to deal with than like 1,010. Piece of advice, doesn't work all the time, but if you get the opportunity to plug numbers in for these, typically 0, 1, those are pretty good numbers to guess typically. They typically make things easier to calculate. Keep that in mind. If we plug in negative 1, then this is just 1. If we plug in negative 1, this is negative 1. So we get negative 10/9 plus 2/3, that's negative. This is going to be concave down. Whoop. Like so. If we plug in 1, which is bigger than 0, 10/9 plus 2/3, this is concave up. Whoop. What if we plug in a number between 0 and negative 6/10? Okay. Pause. Okay, I found a solution. It's not the most fun thing in the world. I'm not going to give you an example like this on the quiz or the test. But if we plug in negative 1/8, which has a cube root of negative 1/2, this becomes a lot easier to calculate. And it ends up being negative. So, what do we notice here? We're concave down from negative 1 to negative 6/10. And then we're concave down again from negative 6/10 to 0. And then we're concave up from like 0 to positive infinity. Remember how I said the first derivative didn't exist earlier for this problem? This is why. Our concavity doesn't change, but there is like a cusp here. There's a corner. There's a place where the derivative doesn't exist. It's a maximum. It's a maximum to be sure, but it's concave down on both sides, so there's a corner. Negative 6/10 is not an inflection point. Why? Concavity doesn't change. It's concave down on both sides. 0 is the only inflection point for this problem because our concavity changes from negative to positive. Pretty cool. I might have screwed this problem up. I'm going to graph it real quick. I'm going to check to be sure. It's a little late. I'll check to be sure, and I'll come back. Turns out I'm an idiot. That's a misfortune. What happens if you set this equal to 0? Let's see, negative 2. This did I? I'm trying to figure out what the problem is. If you check a graph, something that becomes. Wait, hang on, I'm sorry. In my defense, I'm tired. Good news, second derivative, calculated fine. Critical points, A-okay. What do we see here? Negative 1/8, I got that backwards. It should be positive. So we're concave up from negative 6/10 to 0 and from 0 to positive infinity. That's where we're concave up. So negative 6/10 is the only inflection point, and it's at 0 where we have that cusp. And this makes a lot more sense than the other way we had it written up, the other way I had it written up. Because this cusp where it's like concave up, that can be a local maximum, which we know 0 is. So this is something nice. That's a good example for when you're working out these problems. If you already have information about the first derivative, about local maximums and minimums, you can use the second derivative. You can use that to help you find and reason about the second derivative and concavity, and vice versa. If you know a point is a maximum, well, not if you know a point's a maximum. If a point is a critical point and it's concave up, well, that's going to be a minimum. Why? Consider a critical point. Consider a place where the derivative equals 0, I should say. If the derivative equals 0 and it's concave up, well, we have to be a minimum. That's called the second derivative test. It's in your book. You can read about it. Typically, use the first derivative test. It's more convenient. But if you know a place is a critical point and the second derivative's easier to calculate, knowing it's concave up can tell you this is a minimum. Or knowing it's concave down will tell you this is a maximum. But yeah, concavity can tell us a lot about a function just as much as a first derivative can. Definitely graph this one because it's neat to see like, oh, there's a corner like right here, and that shows us where this local maximum is, like it was suggested to us when we did this problem earlier. I'm going to do a couple more problems and then I'm going to wrap it up. Here's a problem. We want to draw by hand f of x equals x cubed plus 2x squared minus x minus 1. How can we do that? We have all the tools we need. We're going to get into this more in 4.5, but this already we have a lot that we need because this is just a polynomial. Okay. We're going to take a first derivative. That's going to tell us where our function's increasing and decreasing. (3x squared plus 4x minus 1). And while we're at it, we're going to take a second derivative too. That's going to be 6x plus 4. Okay. So for our first derivative, we're going to want to look for critical points. Places where this equals 0 or doesn't exist at all. Is it going to not exist anywhere? No, it's defined everywhere. It's a polynomial. We're just checking where it equals 0. 0 equals 3x squared plus 4x minus 1. This might be factorable. It is factorable. I was about to do the quadratic formula for the third time this evening, which is 3 more than I usually like to do it. This should be... hang on. I did it a third time. Critical points, -2/6 or -1/3, and -1. Where are we increasing and decreasing? Let's find out. Number line. Set this up wrong. -1, -1/3. Okay. Let's start with probably the gate. We're going to take 0. Plug 0 into this, we get -1. So this is negative. We're decreasing from -1/3 to infinity. What about something less than -1? Well, if we take like a really big number, 100, 1,000, million, whatever, this x squared is going to be really large, and the 4x, even though it's going to be negative, isn't going to mean anything. So, it's going to be... Is that true? That doesn't feel true. Hang up. No, this is a cube. This is a cube. I gotta keep that in mind. This is a cube. I'll talk about what that means in a moment. Okay, this is gonna be positive here. From -infinity to -1, our function's increasing. And then what happens between the two? Well, if we think about a number between -1/3 and -1, -1/2 comes to mind. So that'd be something like 3/4 minus 2 minus 1, we're going to be negative. So what happens here? Function's increasing from -infinity to -1, decreasing from -1 to -1/3, and then decreasing again from -1/3 to infinity. Okay, so it looks like we're going to have a local maximum at x equals -1 and height, whatever f of -1 is. And we're not going to have a local min or max here. We're going to have a sort of saddled, kind of like x cubed does, just normal x cubed. Okay, so that's cool. Second derivative, this one's going to be a little bit easier on me, which I do appreciate. It's going to exist everywhere, polynomial. We're going to set it equal to 0. And if we solve for x, we get -2/3. We set it up like this. Oops, -2/3. We're going to plug in numbers from either side. Let's take -1 for something less than -2/3. -6 plus 4, that's -2. We plug in -1, we get a negative number. We're concave down from -infinity to -2/3. This whole half of the number line, we're concave down. And from -2/3 on up, if we plug in like 0, 1, 100, whatever, we get positive numbers. We're concave up for all x values bigger than -2/3. How does this help us sketch anything? Well, first let's draw an axis, right? Okay. What's f of 0? It's -1. So let's just mark off a -1, -2, -3, +1, +2, +3. Just put a couple of points in. F of 0, that's an easy one. 1, 2, 3, 4, negative 1, 2, 3, 4. What's f of negative 1? What's our local maximum? Well, it's going to be negative 1 plus 2, so that's 1, minus negative 1. So that's 2. This whole thing up here is 2 minus 1, 1. F of negative 1 is 1, so our height there is 1. Okay. I scaled this a little bit weird. I'm going to redraw it. I realized I botched finding the critical points for the first derivative. I did that now. Also, on an unrelated note, why is this even a book problem? Having to do with 2 times the square root of 7? That makes me upset. That's fine. That's fine. We have a positive, we have a negative, we have a positive. Source, trust me. We're almost done, I swear. This is going to be about negative 4/3. A little bit more. It's going to be like negative 1/2. I'm looking at a graph here. This is going to be about negative 1/2. So we'll say like, say this is negative 5/3. That's going to be right around here-ish. It's going to be increasing, 0, decreasing, 0, increasing again. And similarly, concavity is going to change at negative 2/3. So let's graph some points we know. F of 0, negative 1. Negative 1 is going to be easy to plug into this. We have negative 1 plus 2, so this is 1. Minus negative 1, that's going to be 2, minus 1, 1 again. Okay, so it's going to be whoop, up there. Negative 2/3, not quite sure where that is, but we know that's going to be a concavity change. We know it's going to be an inflection point. And we know that from which this is going to be about 1 minus 2/3, about 1/3, we're going to be having a local minimum. We're going to be increasing. So, we're going to be concave down until right around here-ish. It's not a really good inflection point, but you get the idea. We're increasing through 1. We hit a maximum right around wherever the hell this is. And we start going back down. Apologies, I didn't find a better problem from the book for this. But this is roughly how we can sketch a graph. The first derivative tells us, like, oh, first it tells us like where our local mins and maxes are. It tells us where we're increasing, where we're decreasing, and where we're increasing again. And this tells us where we're concave down and where we're concave up. Pretty cool. I know I'm not exactly making a great case for myself right now, but I'm going to do one more, then we'll wrap it up. We're going to do the weird one from earlier. Okay, showed you this before. X to the 2/3 times x minus 3. We take the first derivative. We take the second derivative. Those tell us where we're increasing, where we're decreasing, where we're concave up, where we're concave down, all of it. And then we graph from that. I copied over all the stuff from the problem from earlier. Me working out is almost as much for me as it is for you. We want to sketch this graph. We want to sketch this function using what we know. We know it's increasing from negative infinity to 0, decreases from 0 to 6/5, which is a little bit more than 1, and then starts increasing again after that. Okay, so let's get started on it. What's our local maximum? It's at x equals 0. First derivative doesn't exist, but the original function does. So there's a point here, and it's a maximum. We plug in 0 into this, we get 0. This is our local maximum. We plug 6/5 into this, we get something that's just about -2. That's our local minimum. I'm not going to ask you to, work that out on your own on, a test. This is our local minimum, right around. This is like 6/5, -2-ish. Okay. So we know from 0 onwards, we're concave down. So we're going to be decreasing and concave down. And then from 6/5 onwards, we're going to be concave down, but increasing. Apologies. From 0 to 6/5, from 0 onwards, we're concave up. Our second derivative is positive. So we're decreasing from 0 to 6/5 and concave up. And then from 6/5 onwards, we're increasing and concave up, shooting off into space. That's what that looks like. Now, what about the other side? We know that we are concave up from 0 to -3/5. So that's going to be right around here. We're going to have an inflection point from concave down to concave up. And we're increasing up this way. So we're going to be, again, this kind of demonstrates there's a cusp here, and this first derivative not existing confirms that. We're going to be increasing from -infinity to 0, and here at 3/5, this is concave up, but before that it's concave down. See how it's kind of bent in a concave down shape when we're less than -3/5, and concave up when we're greater than -3/5, but we never stop increasing? Exactly. This is how we graph things. And this is something I'm going to elaborate on tomorrow for 4.5 when I'm good and rested. But we can combine what we know about the first derivative and the second derivative. We can combine what we know about the local mins and the local maxes to plot points. And we can use what we know about increasing and decreasing parts of the function. This is all increasing, this is decreasing, this is increasing again. We can use what we know about the second derivative, the concavity, to sketch out what we expect the function to look like, more or less. Graph this one in a graphing calculator. See if it looks like this in any way. Try it out. That's something I mentioned it before, but I'm going to mention it again. If you're trying to graph something by hand, always check it against a graph. That's how you learn and practice if you're doing it right or doing it wrong. Okay. I think that's all I have in me for right now. We did a lot. We got through 4.1 to 4.3. I'm probably going to upload these tomorrow morning. Maybe I'll grade the quizzes tomorrow. I haven't graded them yet. I might just save those for Sunday, and I'll just do 4.4, 4.5, 4.7 tomorrow. I haven't decided. I don't know why I'm telling you this. I'm not going to upload this till tomorrow morning. Yeah, well. Yeah, this is going to be uploaded on the Panopto if it allows it, and definitely on the YouTube because that lets me use chapters and I can break this up into the separate problems, and that's a handy feature. Best of luck. I believe in all of you. Good luck studying. See ya.